Yes. So before we start off, we'll just do a quick revision of the stuff that we have been discussing yesterday, and from there we'll just pick it up. So over here, in the last class that we had discussed, is we started discussing about the different kinds of distributions, and we have created the basic idea about distributions like Bernoulli distribution, binomial distribution, Poisson distribution. And on the continuous side, we have discussed about a few couple of very simple distributions like rectangular, the uniform distribution, and finally the normal distribution. Right. So these are some of the basic distributions that we have talked about. And having said that, the next part is today we would be taking up normal distribution at a more, kind of a larger space, and we'll talk about different kinds of testing procedures or different kind of ways through which we can actually test whether a distribution is symmetric. I mean, whether it's normally distributed or not. Right. So over here we would be creating out the framework for conducting non-parametric tests, but we would not be talking immediately about the testing procedure. So we'll talk about the overall idea of testing, right? So, so we'll be talking about the concepts of non-parametric tests today and how is it that we could actually use them to test for normality. So when the testing decision rule and also those will be discussed under statistical inference, right? So let's just start by talking about yeah. So let us just start by discussing the different, the tests of. So basically, let's just have a quick recap of normality as a distribution. So basically, a distribution is said to be normal if it's more or less symmetric in nature. And given that it is symmetric in nature, implies that all the observations are more or less homogeneous within it. That is, there is no such distributional difference in the attribute of the variables. So, for example, say that let's take it this way. So there is this. So there is this distribution, right? So one thing that we can clearly see from this distribution is that to this side of the distribution, so to this side of the distribution, what we have is a scarce compilation of values, right? And over here we have a very or the concentration of the values lie to this specific side, right? So having said that, so therefore these are the two sources. So over here you would see that the characteristic of the values to this side of the distribution is very different from that of the other side. So this part is different from the values at this side of the distribution, right? So this means that these two groups of values, the red and the green, they're two heterogeneous groups of values punched into one distribution. Or I can say that this is a category A. So say this is a category A. This is a category A, and over here this is a category B. So what we can see over here is that both the categories A and B has been plumbed together to create one variable, right? So the one single variable has been punched or has been created by punching in two different groups into one, like punching in two different groups into one, right? So over here, what we are trying to do is, so over here, so in this case, you can see that when two different categories of values have been plunged into one single group, there has been an asymmetry or there has been a skewness in the variable, right? On the other hand, the next part of the variable is, so over here, so we can see that there is an heterogeneity in the behavior of the values, right? So over here, in this case, so hold on. So over here, if you have a look into this value, into the group of these values, you'll see that all the values are more or less similar in nature, and hence I'll say that this series or this set is homogeneous in nature. Right. So basically, most of those variables. So basically, normal distribution. So when I say a variable x is normally distributed, what I simply mean is that the variable value is symmetric in nature. So the group of observation in the variable is homogeneous in nature. As simple as that. And within symmetricity, right? And it is see, and that property itself is called symmetricity, right? And mathematically, the symmetricity is enforced into the function using this particular square. So this is an even function, and even functions are generally symmetric in nature. But at the crux, the entire idea of normal distribution is that it should be it should ideally have a homogeneous group of values. So if a set of variables are homogeneous in nature, that is, they contain variable or observations which are similar to each other in terms of the characteristics, that is where I can say that yes, this there is this test of normality, right? So having said this, we'll come to the next part. Having said this, we come to the next part. So now what I want to know is that most of my theories, like most of my statistical tests, most of my theories, they start on with the assumption that x follows a normal distribution, right? But the question is, where is it that I get to see a normal distribution in real time? Do I get to see normal distribution in risk? Do I get to see normal distribution? If I get to see normal distribution risk, what are the type of areas where I generally get to see? So, and the question is that if I do not get to see normality in a risk data, why don't I get to see? Now just imagine a lending portfolio, right? So basically there are different kind of borrowers who are coming up to a bank and asking for credits, right? Now when this kind of a scenario actually occurs, and when this kind of a scenario is there, then you can expect that there would be heterogeneity in the behavior. And this heterogeneity arises from the heterogeneity in the type of risk. From the heterogeneity, the riskiness of the borrowers. So all the borrowers may not necessarily have similar patterns of riskiness, right? So there might be different kind of sources. There would be different kinds of sources of riskiness, and that is where we want to actually contribute. And that is where we need to understand that what does and how does this heterogeneity in risk arise in a risk data. How does this heterogeneity get dealt with? So over here, let's try and understand this basic part. Let's say there is a credit card portfolio, right? So there is a credit card. So there is a set of loans on credit card, right? So basically, before moving on, let's define the concept of a portfolio. A portfolio is nothing but a collection of loans. So if a bank is given, say, around 2 million loans to has given loans to 2 million borrowers, then the portfolio size in terms of accounts is 2 million. Now comes the next part. That is where so say the loan has been given to different kind of people, right? And this portfolio already has 2 million kind of an account, right? Let's just hold on a second. Okay, okay. So basically, what has happened is, so as I was saying, say there are 2 million accounts to whom I have given the loan, right? Now, on what basis do I know that, or on what basis do I separate the borrowers in terms of their riskiness? So basically, there are 2 million borrowers, right, who have been given the loan. Now, the question that I want to ask over here is, the question that I want to ask is that does all these borrowers have similar riskiness? Right? So do they have similar riskiness? Now, if they have similar kind of riskiness, that means more or less the behavior in terms of almost all the variables would be similar again. So if they are not similar in terms of riskiness, then how do we go about it? So over here, what we do is, so I need to assess that what are the basis on which the riskiness of the borrowers differ, right? So there are various, there are borrowers of different kind of riskiness. Hence, say there is one group which is a high risk. So there is a high risk borrower. High risk. Then over here, what we have is the medium risk. and there is low risk. So basically, there are three types of, there are three broad type of risks that are there. One, there is high risk, there is medium risk, and third, there is low risk. Now the question that comes out over here is that among the high, medium, and low, right? So how do I define my, or how do I differentiate between these three groups of riskiness, right? So a high risk, medium risk, and a low risk. So how do I distinguish? So for distinguishing them, or let's think about it like this: that within the high risk, right, the behavior of all the borrowers in this high risk segment would be very similar, right? Now the borrowers in the mid risk, the medium risk segment will be more or less similar, and the borrowers in the low risk segment will be more or less similar, right? But as I move from the high risk to the medium risk, or from the medium risk to the low risk, I would start observing a significant change in the behavior of the borrowers, right? So basically, say for example, borrowers in the high risk segment will have very high sources of delinquency, very high sources of delinquency, right? So similarly, from the low sources, low risk, you will have absolutely low delinquencies. Have low delinquencies, right? So there is a high risk, there is a medium risk, and there is a low risk. So obviously, you see that if I punch all these three group of borrowers into one single data set, there would be a element of heterogeneity. So what we will observe is there is a huge volume of heterogeneity. So there will be a huge heterogeneity, right? Now, if there is a huge heterogeneity, I will say that the distribution of any variable where all these accounts are punched is non-normal or asymmetric in nature, or it is asymmetric in nature, right? That there is skewness. Now, how do I ensure that there is symmetricity in the behavior? Or how do I know that? So basically, you can think about the within the high risk. So borrowers who are labeled as high risk borrowers will have some kind of a symmetricity in their behaviors, right? The borrowers who have medium risk will have some kind of symmetricity in their behavior. Borrowers who have low risk will have some kind of symmetricity within their behavior. But across the groups, there would be huge fluctuations. So the question that comes out to me is that how is it that this thing actually happens? How is it that how is it that I can actually disentangle these three groups who have having symmetric behavior? So this is where this is where the role of segmentation models come in. So segmentation or business segments, they help us disentangle the heterogeneous behavior within, or the disentangle the heterogeneity in these models, right? So that is where we have the role of segmentation going coming around. So for this, we did develop to understand how segmentation is done within the risk domain. There are different ways of doing segmentation, which we will discuss as we go forward, right? So there is a kind of one good segmentation is a business segment, a business segment, a business segment, right? And the other is or a business segmentation approaches, and the other type of stuff that I have is the other type of stuff that we generally have from there is your statistical segments. There is a statistical segment, right? So one is a business segment, the other is a statistical segment. Now over here, when we are doing this, right? So when we write this part, when we are doing this part, over there we need to understand that there are certain portions, right? So there are certain important stuff that we need to understand over here. That the objective of these segments is to create the homogeneous groups of observations which are similar in types or terms of the riskiness. And when you do this, you know that you have more or less you have ensured more or less normal distribution within the segment. So say there is a variable x. So let me call this variable say utilization variable on a credit card. So what is utilization variable? What is utilization on a credit card? Utilization is nothing but the amount of balance that I have used out of my limit. So basically every credit card comes with a limit, and balance is the balance outstanding, right? So balance by limit is equal to 100. So balance by limit is equal to 100, right? So obviously what happens over there is that I have the utilization over here and the balance by limit into 100. So the utilization rate, right? The utilization rate for the high risk, low risk and the medium risk borrowers will be very different from each other. So generally it can be seen that the utilization for the high risk borrowers will be very low. I mean, will be relatively low corresponding to, I mean, or in relation to the low risk segment. And the utilization for the low risk segment would be relatively high, right? So utilization, so basically there is a low rate of utilization and there is a, so basically the utilization of a high risk segment will be very high and that of the low risk segment will be very low, right? Now, why is this thing actually happening? So if you think about it, you will see that in the high risk segment, what happens is that people are utilizing their card more because why are these segments high risk segment? Because these segments have higher rates of delinquency. So the people are not that concerned about paying back the money. So they are actually utilizing their money and they utilize the card and okay, it's like we are going to pay it back sometimes. So their utilization is generally higher. On the other hand, the low risk segment, which are the more conservative segments, they generally they use their card according to their capabilities. They know that okay, if I use my card too much and then I'm unable to pay, that's a bad thing. So what I'll do is I will now pay my card. So I will pay my stuff So I'll not use to that extent where I cannot, where I would be unable to pay. So what I'll do is I will use my card, right? So I'll use my card and I will pay this, right? So I'll pay as far as I can use. So therefore, the extent or to which a high risk borrower would utilize the card would be relatively higher compared to the extent to which a low risk segment would utilize the card. So the a percentage utilization for the low risk segment would be relatively lower compared to the percentage utilization of the high risk segment. Clear? So over here you have this low risk segment over here, and you have the high risk segment over here. So high risk segment have a higher utilization. Right, so now this is a part where I can actually try and test whether a distribution is, so once I've created the segment, I can try and test whether the behavior of the borrowers across a segment is symmetric in nature or not. So do the variables across, do they generally show that in the low risk segment is the utilization more or less similar? On the other hand, is it the high, with the high risk segment, are they symmetrically distributed? So that is where we can test for normal. That is where we can test for normality, and we can see whether these variable values utilization is symmetrically distributed or not. Right. So if a segmentation has been done, then in terms of certain key variables, the certain key variables should be more or less normally distributed. That is the part where we are looking to contribute next, right? So we need to understand whether a variable is symmetrically distributed or not. And that is where the role of testing for normality actually comes in. So before I proceed, up to this point, is it clear to everyone? Great. Wonderful. Okay. So now I want to test for normality. I want to know whether a variable is symmetric in nature or whether the variable is distributed more or less symmetrically or not. So now this is where the tests for normality come. Now while I test for normality, I start testing for normality, right? So there are a few important logic that we need to keep in mind. Tests. So one type of a test that we have over here is the tests of descriptive statistics. So descriptive statistical measures. So I can look into the descriptive statistics and I can make out whether this is whether the measure is symmetrically distributed or not. So there is a descriptive measure. The second kind of a test that we have over here are the statistical measures. The statistical tests of hypothesis. There are statistical tests. Then within these descriptive measures, there are again two parts. One is the absolute measures of central tendency, the absolute descriptive measures, and the third that we have is the absolute descriptive measure. And the third type of measure that we have over here is the relative measures of the descriptive statistics, or the relative measure descriptive measures. Right. So over here, what we do is we would actually look into each of these measures and we'll test how a normal distribution can be identified. So let's have a quick look into how a normal distribution looks at all. So over here, what we do is to draw the distribution over here. Right. So this is where the variable x is, and this is where the variable fi by n. Right. So this is where the variable fi by n is. Now let us see how this graph looks like. So let's just split this into two parts. Over here, one is mu, median is equal to mode. Right. So there is mean, median, and mode. So the first and the most important thing that we look into is whether the mean equals to median equals to mode. Right. So if the mean, median, and mode are more or less close to each other, then we know that the distribution is symmetric. Now, if the mean, median, and mode are close to each other, that means the skewness or the measure of skewness tends to zero. As such, the extent of asymmetry across the variables would be very less. Therefore, from this condition, it generally follows that sigma is, or the standard deviation is low. That is, if the standard deviation is low, it means that the overall extent of dispersion in the distribution is very low. And when we say it's low, what it means is it is low relative to the mean. Okay. So over there, what we have is mu equals the mean equal to median equal to the mode. Now over here, what we see is then this dispersion, this fluctuation about the central values is the sigma, right? And this sigma is also known as the standard deviation. Clear? Great. Now after this, The next characteristic that we need to look into is, so one is the mean equal median equal to mode, the second is sigma. Right? Now comes the basic measures of descriptive. We now come to the kind of the relative measures. Now what it says is that if the distribution is symmetric in nature, then the median that we have will be nothing but it will be the midpoint of the first quartile and the third quartile. So over here what we have is the median is the midpoint of the first and the third quartile, right? So if the median is there, the midpoint of the first and the third quartile is the median. So first, these two are these three characteristics are the three basic characteristics that we generally get to see in case of normal distribution, right? So obviously, first and the third quartile, the median or the the second quartile being more or less similar, being the midpoint of the first and the third quartile, what we get is that I mean, for a distribution to be for a variable to be normally distributed, get is that the median must be the midpoint of the first and the third quartile, right? So this is what we have over here. Now talking about the next part. Now talking about the next part, that what are the other things that we generally get to see? Now, one thing you will see over here for distribution to be normal, right? You'll see that after a point of time, towards these extreme tail ends, towards these extreme tail ends, right, the distribution generally flattens out, right? So what we generally get to see over here is a flattened down distribution towards the tail ends. Now if you think about it in terms of percentiles, what we generally see is that this part from here, what we have is the 95th percentile and above. So it's like 95 percentile plus, 95 percentile plus. And over here what we have is less than 5 percentiles. Now over 95 percentile or below 5th percentile, the values generally remain unchanged. So one very important characteristic of this distribution, of the normal distribution, is that the 95th percentile plus values and the 5th percentile and values less than the 5th percentile, they remain constant, and that is why the at the tails the normal distribution tend to flatten out. Clear? Okay. So, so any questions up to this? Okay. So let's move on. So from this measure, so if we if we isolate out the characteristics of a normal distribution, the first and the most important characteristic of identifying a normal distribution would be mean equals to median equal to mode. Second will be that the sigma will be less than the sigma should be low, that is low relative to the mean. The third will be that the variable x should be you know the variable x should be like what should I say? The variable x should be the 95th percentile value, and the values after the 95th percentile onwards and below 5th percentile should be more or less constant. And the third characteristic should be that the median should be equals to the midpoint of the first quartile and the third quartile value. Now, if these characteristics are observed in a variable, right, then you can say that the variable is normally distributed. That is, more or less, the distribution is symmetric in nature. Now, observing exact symmetry maybe theoretical is a theoretical possibility, but values near around this is again acceptable, right? So that is one part to it. Now, the second thing that we need to understand over here is the concept of statistical methods of normality. So, what are we need to understand what are the statistical methods that we generally use for model development or for testing for the significance, right? So, the next part is the statistical analysis. The statistical analysis. Now, the question that comes out is how do I identify the statistical or what is that statistical analysis that I need to do in order to understand whether a variable follows normal distribution or not. So over here, the statistical analysis will comprise of two distributions. One is called an observed distribution, known as an observed distribution, and the second that we have is known as an actual or and the next part that we have over here is the theoretical distribution. The second is the observe the theoretical distribution, right? So these are the two things that we are looking forward to. Now, when I say that it's like observed a theoretical distribution, then the next part that we talk about is that what is an observed distribution and what is the theoretical distribution. So the theoretical distribution. Okay, okay. So Kumar has a question. So up to four tests discussed till now. Now, should a distribution pass all the four tests to be a normal distribution or a single test? Now, it happens like this, Kumar, that if it passes one of the tests, and then it would automatically pass all the four tests, right? Because they are of the, they are two sides of the same coin. So if the mean median mode is same, it means that the distribution will be bulged up in the middle portions, right? And hence it will, then there would be no values towards the tail ends, and hence the values would not change towards the tail end. That is, after 95th percentile or below 5th percentile, there would be total standstills. Now, this is what is the overall idea. So, if one descriptive measure passes the test, then that test would be passed across all the possible, across all the possible domains. So I mean, all the tests would automatically be passed. Now, if it passes the statistical test, the descriptive measures test, so when you actually test using the statistical models or statistical methods, you will see that it also passes that test. So because if a distribution is normal, then all these characteristics will always be there. Now we are doing two or three we are doing the checks in two or three different ways in order to ensure that all the results are coming in line with each other. So if test 1 happens, test 2 happens, and test 3 happens, I would know that it is normally distributed. But if one of the tests is not satisfied, then there would be a difficulty. So what we want to do is we want to cross check, we want to benchmark all the tests that are there. Right. So when we do this, you'll see that the entire all the results, they fall in sync with one another. So if one in one case, if it is like if the descriptive measures are passed, then by default you will also see that the statistical models are also passed. Now it sometimes happens that where we generally say that mean equals to median equal to mode, but that is not all. But that's a theoretical possibility, right? So every time you can, it is very difficult to obtain the same variable, I mean the same values across, right? So it's mean, median, and mode to be exactly the same. So what we need to have is that mean, median, and mode are very similar, or they need to be very close to each other. They need to be very similar across this. Now, if that is the case, then what we need to do is, then we need to have this similar factor like mean, median, and mode, and so on, right? So over here, the next part that we need to work around is that, yeah. So basically, say it might so happen that you see that the mean, median, mode values are different, because exactly being the same is a theoretical possibility. It is not always possible in real time, right? So what we do is, you see that A, B, and C, the mean, median, and mode are three different values. But can you say that these different values is very different from each other? So then, to take your decisions, so you say, suppose you see that the mean, median, and mode values are different from each other, right? But you see that your relative measures of distribution, by looking into the relative measures, you see that yes, satisfy these conditions of Q1 plus Q3 divided by 2 is the median, plus 95th percentile and 5th percentile criteria also holds, and so on. But the mean, median, mode are exactly not the same. So then how do you judge that? So if you leave up to only this part, then someone can come across and tell you that, man, though you are banking on the percentile results, I see that mean, median, and mode are different. Can you substantiate the fact that this difference that you are seeing is not, I mean, that is not worth to worry about? So that is where you do a statistical test, and with the statistical test, you benchmark that, okay, this is the statistical test with the result the statistical test is giving, and also by the descriptive measures I can see that both are tallying with each other. So from a theoretical perspective, if someone comes and tells me that like, I do not believe that there is any the difference statistically significant, then you always have a statistical test to benchmark your descriptive results with. On the other hand, if you just provide a statistical test, I might come and tell you, man, this is a biased test, there are so and so limitations, then why will I accept that? So then you have the results on the descriptive statistics to benchmark it against, right? So therefore, these are the two different ways we just benchmark our results. So descriptive measure A gives me conclusion A, or a conclusion B. I see measure B, say measure 2 gives me conclusion B. So if both give me the same conclusion, then I know that yes, this is the same thing. But say suppose I see the statistical models, they reject the null hypothesis. I mean, they reject that the normality. Then I'll say that then I'll also observe on the opposite side that these descriptive measures are also showing the same results, right? So there would not be the case. There would not be the case that in one test result like attests this, the other result rejects it, right? Okay. So now coming to this concept of the statistical test. Now talking about the statistical test, let's see what is it all about. Now, the statistical test has two components. One is an observed value, and the other is a theoretical value. Now the theoretical probability values will be obtained from this mathematical function that we have, and the other will be obtained from the actual or the observed relative frequency distribution. Okay, so as I was saying, so over here we need to talk about these two concepts. One is an observed distribution, the second is a theoretical distribution, right? So what is an observed distribution? The observed distribution is nothing but the relative frequency distribution that you get from the variable, right? So say for example there is this variable x, and you have the frequency over here, and we have the relative frequency over here, right? So we have x, I have is fi, x1, x2, like this. So there are xn values, right? Similarly, what we'll have is frequency distributions, right? So it's f1, f2, So like this we have f1, f2 up to f of n. So the relative frequency distribution is f1 by n, f2 by n, fn by n, right? So over here, f1 by n, f2 by n, so n is nothing but the sum of all the frequencies. So now, if I plot this distribution, right? So if I now plot this distribution on a graph, what I'll get is my observed or my actual frequency distribution. So this will generate my observed distribution. Give me my observed distribution. Observed frequency distribution. So over here what I have is the observed frequency distribution, right? So if I draw this, so over here if I plot this graph, right, with x on one axis and the relative frequency distribution on the other axis, I'll get my observed frequency distribution. Now why is this called the observed frequency distribution? Now this is called the observed distribution because this distribution is obtained from the observed values of the frequency distribution, right? Right, so there is this relative frequency distribution, right? Now from here the next part that we want to do is, so since this is obtained from the actual values, this is called the actual distribution. Actual distribution. Now the theoretical values are obtained from the theoretical frequency distribution. Now if we have the frequency distribution, now from this function when we plot this graph, right, so we'll get the theoretical distribution, right? So the theoretical distribution, the theoretical normal distribution is this part, is this distribution, right? Now our objective is to compare, to know that actually whether this distribution is, it's a normal distribution or not, or the distribution of a given variable x is normally distributed or not. What we'll do is we will compare the relative frequency distribution or the observed relative frequency distribution with the theoretical value, and from there we'll take our decision whether that variable follows normal distribution or not. Clear? So both by comparing the actual and the theoretical distribution, we will try to decide, or we try to zero down on the fact that whether the distribution should be like, so whether the theoretical distribution will be like, you know, so the theoretical distribution will be, so what I mean is, given this variable x, the actual distribution and the observed distribution, we can actually try and find out whether the variable x follows a normal distribution or not. And to do that, we'll have certain statistical tests, right? So that is what we discuss next. So before I just do that, right? Just let me part out for lunch for around like 10-15 minutes, and I'll just be back. And when I come back, I will start off with this question of Aniruddha, that the question that Aniruddha asked me. But I'm sorry, Anirudh, I cannot use an example of Siebel, but I can use another example which I can tell you, right? So we'll use another example from risk and I'll tell you. But till then, just try to be very clear about two things: the observed distribution and the theoretical distribution. When we come back, we'll start off with the explanation as to how the test will be done and how this check will be done, right? So till then, just give me some time. I'll just finish my lunch and I'll be back. And till then, just go through these two basic concepts. Thank you. Hey, hi guys, welcome back. Okay, so all there? Hello, Anirudh Kumar Srinivas. Okay, great. Okay, so as we were talking about it, right? So we were talking about identifying normality using these predictive using statistical measures. So let's start with an example as discussed. So over there, so next part, so happens that uh, let's take the case of a portfolio loss distribution. Let's talk about the portfolio loss distribution. So what is the portfolio loss? So every on a quarterly basis, a bank always incurs certain losses, right? So when I say loss, the loss means the amount that cannot be recovered, right? Or this is what we call the charge-offs. So what is a charge-off? A charge-off actually arises when so basically a charge-off arises when you know when a particular borrower is unable to pay a particular some amount of loans, right? So he is written off, and after that, the next thing that happens is that so basically he's unable to pay back the money, and then some recovery happens. Whatever he cannot pay back, that is actually called a charge-off. Now, these charge-offs are looked into at a monthly level, or to some extent, they're also some are aggregated at a quarterly level, right? Now, now at each quarter, right? So there is a certain so basically there are charge-off lists. So what you have is a value, and you have the respective charge-offs. So over here, so over here, say for example, there are these quarters, and from there you get these loss values, right? Or these charge-off values as we call it. So there are the quarters. So say 2008 Q1, 2008 Q2, 8 Q2, like this. So you have the relevant time periods, and you have the loss values. L1, L2, like this, you'll have all your loss values. Now, I want to know whether this loss distribution is symmetric in nature, or as to whether this loss has a symmetric distribution, or whether it is normally distributed. Now, if the loss values are more or less symmetrically distributed, what it means is that the loss figures have been about has been operating about the business has been operating about its average or its business level or its mean level, and in the neighborhood what happens is the loss distributions get generated, right? So this is what we need to do, or this is what we need to look for. Now if we think about this, so basically what we have is the following. So say I'll just plot the loss distribution. Say I'll plot a distribution like this. Now another way about which we can think about a distribution or an observed distribution is in terms of histograms. So one thing may be possible is that I may draw a histogram, and on that histogram, what if I just superimpose a normal curve, then I can say that then I can, by comparing the two, we can conclude whether the distribution is more or less normal or not. So if the loss distribution, or if the charge of rates are more or less, generally charge of rates are more or less normally distributed across quarters, because as you move from quarter one to quarter two, your charge of suddenly cannot increase or suddenly cannot decrease. Your business operates at a average level, so your collections also occur at an average level, and given your models, your bad rates or your default rates also occur at an average level. Therefore, the overall behavior is more or less very average in nature, right? So having said that, the next part of the story is that there is so if I get to see a histogram, the next thing that I'll go about and do is I'll just map my normal curve over the histogram, and from there we will just cover it out, or we will actually try to find out this particular behavior. So we will try and find out this particular part, that whether the distribution is more or less normal or not. So how do I do this comparison? So let's have a look. So what we'll do is we are just, so we have the quarters over here. I mean, the quarters 2008, 01. So we have the quarters over here and the time, and mean is the relative frequency distribution. So over here, what we do is, so I have a histogram like this. Okay, they're showing me the relative, kind of the loss rates which are there over here. So on the y-axis, I have the loss rates and over the loss rate and the frequency distribution. Over here, what I have is the behavior of the data, right? So this is how the histograms look like. Now this is my observed distribution, right? So the next part that happens is I take out my theoretical distribution, which is the normal curve. So what I do is I take that and I place this curve over. So after doing this, what I can see is that there is a substantial part of this distribution which lies below. I mean the observed distribution which lies below this histogram of this frequency curve. Now if this lies below this, then the next part that implies over here is, the next part that I have over here, the next part that we can say over here is that I can see that a large part of this distribution is covered, falls under the theoretical curve. Hence, my conclusion is that this distribution is normally distributed. So this is a very simple, and this is a kind of a visual exercise, right? But this is not per se statistical, because if there is statistical, I need to test for the significance of this distribution in all the statistical sets. So there is this normal distribution. So it's a graphical measure using which I can actually comment. So over here, how do I incorporate the concept of a statistical test? So before I go into that, can you tell me as to whether these concepts, observed distribution, theoretical distribution, this example of loss distribution that I talked about, and this graphical and the test using the graphical measure, is this part clear to you guys? So are you able to get the idea now, Anirudh? Does this example answer your question? Great. The others, is this idea clear? Idea of observed distribution, the idea of theoretical distribution, and the idea of this way, the loss distribution example, and the way this graph is constructed. So are these clear to you? Great. Now, now what we need to do is we need to develop a statistical measure or a statistical test. So how do we develop this statistical measure, or as we call this, statistical test? Okay. So over here, what we'll do is we'll do the following. So let's think about this. Now, to derive a statistical test, I need to define two things, rather one thing for the two distribution. That is known as the cumulative distribution function. Distribution function. So, do we know what a cumulative distribution function is? Okay. So, a very simple way to understand cumulative distribution function is another frequency table. So, let's look into this table. It's There is Fi, right? Then there is Fi by n. This is where the relative frequency distribution comes. So x1 occurs with a frequency f1. What you have is x2 with a frequency f2. Fn. So over here what I have is f1 by n the relative frequency is f2 by n fn by n, right? Then what we have is the cumulative distribution function, that is CF. So the first level of cumulative distributive function is f1 by n. So what it tells me is what is the probability that there is a number x which is less than equal to x1. Now over here, the next part what it tells me is what is the probability that the variable x a value which is less than equal to x2 is equal to f1 by n plus f2 by n, right? So the next stage like this, when I calculate what is the probability of x less than x3, then it is like f1 by n plus f2 by n like this up to f3 by n. So similarly like this what happens is the probability x less than equal to xn, that is equal to f1 plus f2 is equal to f1 plus f2 divided by n. So therefore what we get over here is that this is equal to 1. So the cumulative distribution function does nothing but it gives me an idea about the probability of x less than equal to a xi. So if I draw this graph, over here, if I just draw this graph, so between 0, so over here this is x1, over here the number is x2. So like this I have the value till xn. Over here say what is the probability that x will take a value less than equal to x1. So the first value that it starts off with is x1. Now if if the first value starts off with x1, therefore it is not possible that x will take a value less than equal to x1 or less than x1. So therefore the probability is 0. This is your relative frequency distribution or Fi by n. Now, when it happens, now what is the probability that x will have a value less than equal to x2? So it is nothing but the probability of x1 plus the probability of x2. So therefore there will be a discontinuous part, and we'll have this value. So between x1 and x2, this is the probability of getting an x less than equal to x2. Similarly for x3 again, there would be a discontinuous portion over here. Between x2 and x3 will be another value. Like this, it will go up, it will go up. So the point where this value hits the last value is 1. So the probability that x will take a value x less than equal to xn is 1, because x takes all values between x1 to xn, or only values that x can take is between x1 and xn. Therefore, probability of x less than equal to xn is what we have over here, or what we see over here, right? So this is how the CDF, or the cumulative distribution function, or the observed cumulative distribution function, will look like. Cumulative distribution function. Right. So this is the observed cumulative distribution function, which is created from the observed frequency distribution. Now, similarly, a theoretical cumulative distribution function can be generated from the normal distribution, from the function of the normal distribution, from the PDF of the normal distribution. So that is plotted as, or that distribution of the cumulative distribution, something like this. Now what we need to test over here is that whether the difference between this cumulative distribution function and the theoretical cumulative distribution function, whether this difference, the difference between this is significant or not. So how is it that we would know that this difference is significant or not? So the difference between the theoretical and the observed cumulative distribution function. So if this difference is significant, then we can say that yes, this distribution, then the observed distribution does not approximate to the, no, the theoretical distribution, which in this case is the normal distribution, right? So up to this point, is it clear? Okay. Okay. So any other questions? So to your question, Anirudh, cumulative distribution is taken because whenever we want to compare any distribution, right, we do not compare the PDF or the shape of any, the exact shape of any distribution. What we do is we use the cumulative frequency curve graph, right? And when we use the cumulative distribution. And over here, if you say that, so I did not understand the second part to your question, why not normal distribution? So the red line that you can see, that is the cumulative distribution function of the normal distribution itself, right? So, so the first over here you have the observed distribution function, and then you have the CDF of the reference distribution. So this is the CDF of the reference distribution. Now, when I talk about reference distribution, what I essentially mean over here is that the difference, so if you want to test whether this CDF replicates the or is very close enough to the distribution of the norm, I mean, whether it's very close to the CDF of the normal distribution, then we say that as a reference distribution. So if I want to find out whether it is significantly different from normal distribution, then the CDF of the reference distribution should be the CDF of the normal distribution. And when and the cumulative distribution function of the observed distribution is concerned. Now the difference between these two distributions are found out. So what is the difference between the observed cumulative distribution function and the CDF of the normal distribution? Now, if that difference is found out to be significant, then we'll say that yes, this model is, I mean, yes, then this distribution, observed distribution, does not follow a normal distribution. So what are we trying to do over here? We have an observed distribution value, right? Now we are trying to test whether that non-observed distribution is following a normal distribution or not. And that is why the reference distribution over here for us will be the normal distribution. So on one end, what we do is we use the cumulative distribution function, which is shown by the green stepped graph, and we use the cumulative distribution function of the normal distribution, which is shown by the smooth red graph. And we compare whether the difference between these two functions, or these two uh, cumulative distribution functions, are significant or not. Yes. And this kind of a test which we are using to kind of predict as to what so whether a particular distribution follows a given reference distribution. So this kind of tests are known as the non-parametric tests, because in this test, if you observe, we are focusing on the observed distribution, right? And we are trying to understand whether that observed distribution follows a reference distribution or not. We are not parametrically assuming that X has to follow a given distribution. We are testing whether X follows a given distribution or not. So in that case, this kind of tests are known as the parametric tests. Clear? Clear up to this point. Great. So with this, we come to the end of our discussion on probability distributions. So we have completed the measures of descriptive statistics, which included measures of central tendency, measures of dispersion, and we have also completed the probability theory, right? Within probability theory, we have completed the concept, the basic theory, the classical theory. We have completed the axiomatic theory of probability. We have completed the mathematical theory of probability. Then what we have also discussed is the distribution side, where we have discussed on the basics of continuous and the basics of discrete distribution. So in discrete distribution, we have talked about Bernoulli distribution, binomial, and Poisson distribution. And in continuous distribution, we have talked about the rectangular distribution, uniform distribution, and the normal distribution. With normal distribution, we have talked about how to test for normal distribution using graphical methods, statistical methods, I mean, descriptive measures, as well as statistical methods. Now, once that has been done, the next part that we move into, or the next part that we move to, is the theory of statistical inference, which we do in the next session. So the next session would be held before Saturday, right? So we would be doing this session on Wednesday at 9 p.m. onwards. 9 p.m. Sorry, 10 p.m. onwards, right? So please log in, right? And in that group, please set out a message that next class to be held on Wednesday at 10 p.m. Just put that message in, so that will be a reminder for me as well. Okay. So thank you guys. Please do send out that, just to ping it that we'll have the class on Wednesday, and then we'll get started with it. Wednesday we start talking about the statistical theory of inference, where we would be talking about sampling theory, we'll be talking about the estimation theory, and we will be talking about the elements of testing and hypothesis, which would be followed by discussions on logistic linear regression and logistic regression. Thank you. So I'm done mostly from my end. If you have any queries, write into me, and I'll share out all your study materials and recordings tomorrow. Thank you. Bye bye. Have a great week ahead, and let's meet on Wednesday, 10 p.m.